All right. I want to talk about another application of calculus, and this is sensitivity to change. And the question here is, how sensitive to a change in one variable is another variable? So how does changing one variable affect another one? And this is used pretty frequently in industrial engineering, medicine. One example that I've seen has to do with how does changing a dosage of a medication affect patient's temperature? And you want to know how sensitive changes in dosage or temperature is to changes in dosage. So the example in the book, which is example 6 on page 135 of our AP Calculus book, is the experiment about smooth skin versus wrinkly skin peas. And it's interesting because historically, this had to do with hybridization. One of the first experiments on actual hybridization. And we've got two variables that we're going to define. And one is the relative frequency of smooth skin gene in peas, and that's called P. And the other one is the proportion of smooth skin peas in the next generation, and we're going to call that Y. I'm not going to get into the details. Suffice it to say that the proportion of smooth skinned peas in the next generation can be modeled with this equation. As you can see, it is in fact dependent on the relative frequency. This graph, when we graph it, looks like this. And what you can see is immediately just looking at this graph is that when the relative frequency is low of this gene, changing that frequency just a little bit will make a huge difference in what happens in the next generation. This is a steep graph, and this is not a steep graph. So if I graph the first derivative, the actual derivative, what I get is I get this, and you can see, hopefully, that up here, that a small change in P, the frequency of the gene, leads to a large change in what happens in the next generation. All right, I'll be back with the last video before the recap, and we'll look at economics as one more example of how these kinds of things are used.